Something you may have noticed in the previous episode is that in our implementation of the recursive binary digit parser, we did something like this. We said decrement the count of the digits. Now in this particular instance, this reads in order. And so stringing together function invocations like this is still pretty easily legible. However, there are times where this reads out of order, and that's a problem. Related to that problem is the fact that in traditional JavaScript, if you want to perform multiple consecutive operations on a collection, or any value really, you can use dot notation and string these invocations together, and it reads very idiomatically, and it reads in order. So this is very nice, but in the functional approach, we don't want our functions hidden behind data structures. We don't want to have to access them through dot notation. We want them to be first-class citizens. However, this can result in something like this. If you wanted to do the equivalent of this operation in the functional approach, you would end up writing this, which reads out of order. Because we're not reducing and then filtering and then mapping. We're mapping and then filtering and then reducing. But if you don't keep track of how it's nested and keep track of when the parentheses open and close, this reads out of order. And this can easily get confusing. So how do we keep the functional approach? How do we keep our functions as first-class citizens and without having to compromise on legibility and idiomatically stringing function invocations together? We still want to be able to read function invocations in order even if we string them together. Clojure has found an answer to this problem, and it's called thread operators. Now, thread operators come in different shapes and forms, and one thread operator, for example, is this one. It's called thread first. There's another one that looks like this, thread last. And what these operators do is they solve exactly this problem. Now, the way we're going to invoke them looks like this. To do the same thing that we did here, we're passing in the item that we want to perform some string of operations on first, and then we pass some arrays that represent function invocations. So if you can mentally replace these brackets with parentheses and move the first parenthesis after the first argument, you can start to see how this first argument resembles a function. In fact, it is a function, and is going to be invoked as a function. Now, what the thread last operator does is it takes the first value that we pass in, and it passes it as the last argument to this first array. Let's call it v1 here. And then it's going to invoke map with the arguments inc and v1. Then it's going to take the result of that invocation and put it at the end of the next collection here. It's going to invoke filter with even and that result v2, and so forth. It's going to keep going until it's run out of arrays here. So do the same here. Now, but the advantage of using the thread last operator is that you don't actually have to put these intermediate values in here. Now, notably, you can then also pass in other functions that don't have anything to do with arrays. For example, at this point, we've reduced plus over this collection, so now we're dealing with numbers. So let's say if for whatever reason you wanted to increment that number, you could do that here. Now, you can pass this as an array it just doesn't take any additional arguments. Or because it doesn't take any additional arguments, we want our thread last operator to be implemented in such a way that it recognizes this as a function, even though it's standalone. And then you can keep going, and these can be mixed too. So if afterwards you wanted to multiply that number by 5, that's how you could do it. So this is basically how we want to be able to invoke the thread last operator. So how might we implement this? One more thing I should note, by the way, is we've stumbled upon something here that is pretty cool. And it's kind of what Clojure is all about, namely being able to programmatically build up expressions like these, data structures like these, that resemble code. And in Clojure, they literally are code. But here, they are later turned into code, and we interpret these as code. And you could imagine that if you can, this gives you additional power over how you write your programs, because now you can programmatically write programs. Because all you have to do is you have to build up these data structures, and they're just arrays. So you can use map, filter, reduce, and so forth on these structures themselves, pass them to a thread last operator, and then evaluate them. So this gives you an entirely new tool. Okay, so how might we implement the thread last operator? So one thing you may have noticed as I was talking about how the thread last operator works is that at every step, it takes the result from the previous operation and passes it on to the next function invocation. This should sound reminiscent of reduce. And it is. That's exactly what reduce does. So this is a clue that we can implement the thread last operator in terms of reduce. So let's say thread last, a double underscore, is a function. And what is this function going to take? It's simply going to take some initial value, and then it's going to take an arbitrary number of expressions. We can call it that. And then, as I said, it's going to reduce. So we're going to return the result of reduce here. Reduce, as always, takes as first argument an anonymous function. Well, it doesn't have to be anonymous every time, but in this case, it's an anonymous function. And as always, it takes an accumulator and the current item that we're iterating over. And we are reducing over the expressions. And as initial value, we pass in literally the initial value that we're concerned with for the thread last operator. Okay, then what is it that we want to do? Well, note that I said that if something is passed in as a collection, then we treat the first item as a function and the rest as parameters that we're passing to that function, and then we invoke it. If the thing that we're iterating over is not a collection, but instead a standalone item, we treat it as if it was a collection with only one item. So we have to distinguish here between these two cases. We have to check, is cur a collection, or is it an array, or is it a standalone item? So let's make a helper function. It's called isCall. And for now, we're only, of course, there are other types of collections in JavaScript, but for now, we're only concerned with arrays. So we're going to assume that whatever is passed in here is an array, and we're only going to return true in isCall if the given parameter is indeed an array. So if the current item is an array, we're going to want to treat the first one as a function and the rest as parameters, like I said. And if it isn't, we're going to want to do something else. And actually, this case, when it isn't, is simpler. So let's do that one first. When it isn't a collection, that means that cur itself is a function. Because each line here that we're iterating over is cur. If it's not an array, it's going to be a function itself. So we can use cur as a function and invoke it. What do we invoke it with? With ACK. Because ACK, the accumulation, is the result from the previous iteration. And we have to return that. Okay. Now, if it is a collection, as I said, then the first argument is our function, and the rest are function parameters, and we have to manually append ACK to that list of parameters. So how might we do this? Well, we can simply use this nifty syntax to get the function out of, and the function and the arguments out of the current item that we're iterating over. Because again, the first item is the function, and the rest we're going to treat as arguments that we're going to pass into that function. And then it's really simple. All we're going to do is invoke that function with those arguments and our accumulated result last. That is why it's called the thread last operator, because we pass that in last. And that's basically it for the thread last operator. There's not much more to it. So let's try this out. So thread last is loaded. And let's try something like what we had before. Let's first give it some collection of numbers. If we only pass that collection of numbers, it just returns the collection of numbers. So that's great. Now let's say we want to map ink over that collection of numbers. That works great. And now let's string together additional function invocations. Let's say we want to, of that, we want to only keep the even numbers. And this works also. And let's say of that, reduce it using plus. So I hope this is starting to come together. Like we can now iteratively add more stuff to this chain of invocations, and it all reads in order. Let's increment that number, and let's multiply it by 5. So thread last is really a very simple function actually, but it gives you a very powerful tool. Now I said that there's also something called thread first, and the difference between thread first and thread last is basically in this line right here, because thread first, what it would do is instead of putting the accumulated result at the end, instead of putting it here, it would put it at the beginning. It would pass it as the first parameter. So it would look like this instead. But everything else would be exactly the same. In the case where we're not given an array, but a single, or it's just a standalone item, well then we're only passing one parameter anyway. And so the first and the last one are the same because it's only one. So there's no difference in that case. But because thread first and thread last only differ in this one regard, in this one line, I suggest that we, instead of copying all of this to create the thread first operator, which we could do, right? We could say thread first is did I do that right? Yeah. So now these two lines are that's the only difference between the two. So we're reusing a lot of boilerplate code here. So I suggest what we do instead is wrap this entire thing in a function. And let's actually call it thread. And instead of making, so it's going to return this function, and it's going to take a type, and this is going to be either first or last. And then it's going to return the kind of operator that we want as a function right here. And then inside our thread function, inside our thread operator, this function here, and in fact, inside the reduce call, we can now distinguish at the line where it matters. And there's different ways you could do this, but I'm going to use a switch operator, and I'm going to say, depending on the type, which is either first or last. If it is first, what we want to do is return f with ACK passed as the first argument and then the remaining arguments. If the type is last, what we want to do is invoke f with the arguments that were given and then ACK as the last argument. And then what we can do is we can simply declare let thread first, so a single underscore for thread first, is thread first, and a double underscore is thread last. And so that's really, that's it. That's the entire function to create both thread operators. And let's see if they both work. So let's try what we had before. Let's say 1, 2, 3, 4, 5. I'm going to try the thread last operator first. Let's say we want to map ink over it. That worked great. And let's say we want to filter and keep only the even numbers. So this seems to be working. And let's say we're going to use the thread first operator. And let's see, what might we use this on? We could say, actually, I just had an idea to illustrate the difference. Why don't we make a helper function called greater than that takes 2 arguments and returns whether or not the first one is greater than the second one. And just to illustrate how thread first works, let's also create a last function that simply returns the last item in a collection. We could either write this like this, but we can also write it like deck count of the collection. But now that we have the thread first operator, we can actually write this as call count and then deck. Oh, sorry. We can write it as call at call count and then deck. Okay, let's run this. And let's run, say, a thread first operator with, I had an array of ages prepared, but let's say 1, 2, 3, 4, 5. And then we take the last one. So that worked. And then let's say we want to check whether or not it is greater than 17. So you can see here how the difference between thread first and thread last matter. Because thread first is going to put the result from the call to last in here, right between greater than and 17. Whereas thread last is going to put it behind 17. So thread first is going to check, is 5 greater than 17? Whereas thread last is going to check, is 17 greater than 5? So if we run the same thing with the thread last operator, it's going to evaluate to true. So there you have it. Not only do we get idiomatic reading in order functional style programming, but we also get an entirely new way of programmatically constructing our programs. And I highly suggest that you keep this in mind because, as I said, this is what Clojure is all about. And in fact, this is a core feature of any Lisp language, which Clojure is one dialect of.